is happening.
What?
I can. It's close to it.
If your eyes are bad, sit close. Why do you choose the farthest seat?
This is where I sit for PK's class. It's where I have all my stuff on here. My computer.
All right. Okay, so Metzley is going to tell us about numbers and accuracy of those numbers. As I was pointing out, there are student help sessions. Trinity and Metzley both popped in and they were on Zoom and they just asked me questions, then they left and they were very happy with the response. It was helpful. Okay.
I can hear yes.
I didn't hear a yes either. I heard the absence of a no, which is not a yes. So generally speaking, if you have questions, they're here. Sometimes I'll do the Tuesday, Thursdays in person, but just pay attention on Slack. Today we are going to be doing 4.1 to 4.2, talking about accuracy and speed. We'll do a couple pair exercises, and then this week's homework is one on visualization and one on using accuracy and speed. Okay. Any question before we get started? Do you want me to start by putting this up, or do you want me to start by putting the book? We can have both up. Hold on. See, I can. Where do you want to start? Is there a page? That work okay? Please hold. Metzley's going to present, but she needs water. Yeah.
After discussing how computers have limitations, so to describe how computers are accurate and fast enough for the calculate computer languages. So the first example that I'm going to do is comparing like two numbers. So in Python, the text says that it's 10 to the positive 308, and that's the positive largest number that Python can use, and the largest negative number is negative 10 to the 308. So on my code that I have.
I got it.
Basically, we're floating the limitation. So basically what that means is that there is a limit to how large the floating point number can be. So overflow happens when the value is the largest or smallest number. So as you can see here, when you print like an overflow, or if you multiply that positive number, which is 10 to the 3 by like basically any number, like if it was 7, 8, like after the overflow, you're gonna basically just have infinity. So that's like if there, if you go above that number, you end up with infinity, or if you try to like multiply it, it will also be able to add something to this thing. And then, for this next part, I did it with complex numbers, which is what the text is also describing. If you multiply it to a complex number, you're also going to end up with a number because of that equal. Because that number that we started with is canceled zero, so you can't really go against that. So basically, the text is just saying that there's limitations to the numbers that we multiply. There's also in this way, which is talked about in the text. So if we're going to do it in this way, it would be the number that I use, which is in the text, is 10 to the negative 308. So if you try to divide that, you end up getting 0. So why use it as like a very small number, zero, something. So it seems so Python will give a standard level of precision to a maximum of 16 significant figures. So the example that the text gives is when you add 1.1 and 3.2, so you should get 3.3, but Python is going to give you digits like that are more precise. So I think the text it gives you up to like 16 digits after that, so 3.3.
Yeah, it's over here. So it should be 3.3 exactly, right?
So it's basically saying like you can't put an if statement in order to fix that. So there's no if statements in fixing that. Rather, in order to fix that, if you want like if you want x to equal 3.3, like you have to use that other code that's down there. Yeah. In order to fix that.
Can you walk us through this?
So that's one.
Okay, so let's look at this section right here, right? And just remember our scientific notation. So this is the true value of pi. Pi goes on forever. And then here's the value that's stored in Python. And of course, we can count. So this is 10 to the minus 1, 10 to the minus 2, 10 to the minus 3, so on and so forth, right? So we can say something like epsilon is 1e to the minus 12, which means 10 to the minus 12. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that means we have 12 decimal places of accuracy. What this says is as long as the difference between your number and the number that you want is smaller than the accuracy, as long as the difference is smaller than 10 to the 12, then I believe they're the same number. Whereas up here, this says, are they exactly the same? And that's not always the case because of these changes down here. Right? Okay. So generally speaking, you'll do perfectly fine. You know, if you have something that says, you know, if they're equal, you know, 2 equals 1, or, you know, 1 plus 1 usually equals 2, right? Almost always. But sometimes it equals 2.000000000000001, right? And that is just the nature of getting rocks to think, right? Okay. We have an example here.
I have two different values.
Mm-hmm.
So when you calculate y minus x, you get 1.25. So instead of this 16 significant figure accuracy, there's like a 7% fractional error, like in this case.
Wait. Can you scroll up? Can you show them this one? Because that's fucking sick, right? So walk them through this one here.
So that one's giving you the answer to 16.
Yeah.
Instead of what you would get for the first one.
Yeah, so everyone knows that 1.1 plus 2.2 is 3.3. So that's what this is. So you expect that number to be 3.3, right? But since you don't print it right away, you don't actually know if it is. And in fact, if you were constantly printing out everything you ever did, you would get annoyed. There'd be too much output to the screen. So then we say, here's the accuracy that we want to set. 1e to the minus 12, right? And it says, if the absolute value of x, whatever that is, minus 3.3 is less than that amount, then you print it. And it was, so we printed it, but look at what it was. It wasn't 3.3. It was 3.3 with a bunch of zeros and then a 2 or a 3, right? This is all that you put into it. Right? Computer is just adding weird stuff. But why are they doing it? Why is the computer not giving me what I want? But I didn't. All I gave was this. 1.1 plus 2.2. Too big? Let's see how many digits of accuracy. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. It's only a mistake in the 16th decimal place. What's happening? Yeah. What's physically happening in a computer when it records a number? Good. Up and down something, right? Oh shit, all my favorite chocolate's gone. What have I done? You moron. Okay, wait, hold on. I got it. Okay. What is this number? 0. Very good. What is this number? What? 1. Very good. What is this number? Wrong. 2. We are counting like a computer because computers only know open, closed. So essentially what they're doing is they have some electrical gate and they either have it open or they have it closed. But what we don't see here, okay, check it out, is 0, 1. What did I do? 0, 1, right? Okay, unfortunately, there are bins. Okay, have you ever heard of like an 8-bit computer or a 4-bit, right? That represents how much memory. And the amount of bits represents how long a number you can store. So if I go to the next one, I can do 1, 1. What number is that? 3. Weird, right? Very annoying, very stupid. Okay, what's the next one? 1 0 actually is next. What's that? 4. Good, right? Now, I don't know if these are 100% correct, depending on what you have in your computer, right? All of these bits are different. But if you have a longer number, right, you can go 1 0 1 0. And binary will read that as a number. Every bit that you add increases your accuracy by a factor of 2, right? Your first choice with only 1 bit, you can only pick 0 or 1. With 2 bits, how many choices do you have? 4. What 4 numbers can you create with 0 and 1? Right. Make sense? Dumb, right? But it's right. So now let's imagine you have a fixed number of bins. Okay. And at the very beginning, I put in the number 1.0000000. Okay. And I add to it 2.0000000. Right? Assume I did that in bins too. What is the answer? Correct. Right? Except no, that's wrong. Right? That's what's so crazy about this. You expect it to be right, but it's wrong. And so now my question goes back to, how the fuck could it possibly be wrong?
The binary code for that placement didn't have, it had to do a 0 or 1, it just isn't.
I think you're thinking very rationally about it. Got plenty of bins.
Rationally, it's stupid.
Irrationally, it's stupid is the right answer. Okay, and let me tell you why. What is a computer made of?
Rocks.
Exactly right. It's made of rocks. And rocks, especially electronics, are subject to what processes? Do you have a name for that? It's tricky, right? What? Random error. I love those words in that order. Okay. So in fact, the rocks are governed by quantum mechanics, right? And sometimes you get charge where you didn't expect charge to be. Just randomly. A qubit, like a quantum computer, has superposition. I'm just talking about the fact that you could just have electrons that just jump from where they're supposed to be. They just jump to another place. Because who fucking cares, right? That's like what electrons do. They just do their own things. And sometimes they just jump. And so you might have one of these gates way down here, just like on its own, be like, whatever, I'm a 1 now. Does that make sense? Okay. Is it what you expect? No. Does it make sense? Yeah. Right? It's the limitation of using rocks to do thinking. Right? When you write it down on paper, it's much easier to get it right. When you write it down on rocks, rocks they interact, they're physical objects. They have limitations. They're subject to quantum mechanics themselves. And, you can have a disk writing error. So there's a physical thing called the disk and a laser that you shoot on the disk in order to record those numbers into random memory. If there's a small mistake, it's going to click the box wrong, right? It's rare, but it happens. If you take a hard drive, okay? Let's say you take your hard drive from when you were a kid, and it's got all your favorite games on it. And it's been 10 years since you turned it on. Is that still usable? No, all that data is gone. Did you know that?
I've had my hard drive for a while.
But if you turned it on, yes, if you don't turn it on for 10 years, right? What happens is, so inside your hard drive, it has self-corrections. What it does is it makes sometimes 2 copies of something, and it looks to make sure that bits didn't actually switch. And if they did, it switches them back, right? That's part of your solid state device. But if you don't power it on for a really long time, you can lose the data simply because all of the ups and downs get flipped. Isn't that weird? This doesn't happen frequently, obviously. Nobody just leaves a hard drive around for 10 years and then needs something on that hard drive, right? Okay. Does this process make sense? Why this is so strange? Sorry, I didn't mean to derail you, Metzley, but okay. Where do you want to go next? Oh yeah, let's do this one. This one's a funny one. No. Can you do that other example first?
You should get. Or.
So this is a weird number, right? How many zeros are here?
Wow.
A lot. Good, very good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Good. Okay, what about this one? A lot more, right? Does Python ever get mad at you for how many digits you can write? Did it say you couldn't do this mentally? No. Right? I can keep writing, right? I could write all of the digits of pi that I could possibly write in a human lifetime, right? And then I could load it into memory. And what would it do? Yeah. Yeah, literally, it just says, fuck you. I can only do this, right? And it does that. It just says, fuck you, it gets rid of all these numbers, and then it does the difference, and what do you get? 1.25. Is that right?
Kind of close.
Good. It's kind of close.
Good enough for government.
It's good enough for government, right? It's a C plus, right? Okay.
This one. But it's supposed to be.
Yeah, so let's pause. Let's see if we understand that. Do we see what's happening here? No. Metzley, do you want to walk Trinity through this? What's the first line say?
Right, so. Right here, it's saying that we see that this expression right here gives us this square root of 2. So this right here is basically what we're trying to have to equal the square root of 2. So the square root of 2 should equal the square root of 2, but it doesn't. We have 2 different values.
Right? Because this part here is x. This is the y. And you can do these, right? Do these with your hand. What happens when you multiply this times these? What's y minus x, by the way? No? Y minus x? What's that? Yeah, so it's 10 to the minus 14 times the square root of 2. Good. So that's what y minus x is. And then you multiply it by 10 to the 14, 10 to the 14, and 10 to the minus 14. They cancel, so you should have square root of 2. We all agree, right? And yet the computer says? Survey says? You fucked up, right? So what happened?
Information. And when the pen mouse work.
Doing the what?
Like when it's going through the work of the first one, maybe it's not carrying as much information.
Going to the work of the first one of this one?
The print, the first print.
Yeah.
Use this trap.
Yeah, I mean, let's have a look at this one. Can we print y, Metzler? Just, yeah, just right below this, can you just print y?
Like type in.
Yeah. Oh, it's gonna yell at you because this is. Yep. Okay. Oh god. Okay. Oh god. Why is it getting so big and towards me? Okay, do you see what this is? What does this remind you of?
Like similar to like the previous cell, but before it brought out the output.
Yeah, if you scroll up. Yeah, right? Doesn't it look a little bit like that? When we already knew that it was going to be real dastardly and rude to us. So if we scroll down, we can see that the first thing that we loaded into memory could only hold on to 16 digits of accuracy. And yet, we put all the important information at the very end. Right? So look at these three numbers, 1, 4, 2. Okay? Look at what numbers actually show up. 1, 4, 2. Oh shit, that's where the numbers come from. And look at this gobbledygook that comes after. That is just arbitrary. That is whatever happened to be loaded into the memory of the computer, because it does not know what happens after the 4, 2. Someone write down just the first three numbers here, 108. All right, or I guess we can remember them. Now, Metzli, can you restart the kernel? So restarting the kernel will delete everything from memory. I hope. And then only run this last one here. Okay, they made the same mistake twice. I wanted to see if these numbers would change. They didn't.
Stubborn.
Stubborn. Yeah, exactly right. Okay. How are you feeling about that? Anything else you want to say here? So which one? I don't think we have more time for. You're talking about these ones here? Talking about the errors, rounding errors. Here we're running out of time here. And the most important thing to get away, like we haven't really gotten into program speed and we won't in detail, It's really just working, like breaking the computer is what we want to focus on today. So we're going to break into the same groups that we did from Monday. And what I want you to really be working on here is understanding the intellectual limitations of the computer, right? So when you get something that you didn't expect to, don't be surprised, right? You started off not really knowing how to do Python. That's okay. Maybe you didn't really know how to do computational physics. Now you're kind of learning both. And I'm warning you, as you do that, one of the most important things is how do you know to trust your output, right? Because not only am I telling you that you could have messed up, now I'm introducing the fact that the computer may have fucked up, right? So that's even more disconcerting. Okay. We're gonna talk about like approximations and whatnot on next Wednesday. So next Monday, for example, we don't have class. Just it's President's Day, I think, or something. Yeah, President's Day. So we'll come back to this idea. If you're having trouble with it, let me know. Look at section 4.1, 4.2. Okay. Anything else you want to add, Metzling? Okay. Everyone happy?
This is like, if you're limited by the computer then, or people who do like actual rocket science, right? What do they do then? Do they just have an arbitrary error percentage and then they're okay with it?
Yeah.
And that's it?
Yeah, the world rides on arbitrary errors. They're called thresholds, right? And so you build in some, so for example, let's say you're designing a bridge, right? You build a bridge and you expect that it is going to flex and it is going to change. And so you build into the bridge, into the design of the bridge, places where if there's any sort of collapse, those things break first and the whole thing doesn't come down, right? Similarly, we understand how computers work quite well. So we understand that if we have some number represented, right, and it's very long, that we may have an issue with its accuracy. So we characterize the errors such that we say, well, we can't know everything infinitely well, but we know it to within a certain amount. And so what you can do is you don't run a simulation once, you run a simulation 400 times. And you see how frequently do you get the same answer, right? And then you can say, okay, well, some of them went off in the wrong way. Those totally failed for whatever reason, but a majority of them, they did really well. Make sense? Okay. Okay, let's do, we're going to do 4.1 and 4.2 today, I believe. Is that correct?